There we go. Custom PCB design. This is not the way I expected this channel to be going, but here we are, working on custom schematic design and PCB design, all because I wanted to put a brake light in my car. Amazing how things take a path that you never expected, right? All because, of this little bad boy. Deciding that I wanted to put a brake light in the ducktail spoiler of my 350Z was one of the first things I did on this channel. Subsequently, I had maybe 40 followers when I first introduced the project, and we've got quite a few more now. So just for the sake of everybody who's catching up on this ongoing project and what it's migrated into, let's just take a quick look back through what's happened so far. It all started innocently enough. I bought a ducktail spoiler for my 350Z, as many people do. But being the kind of person that I am, I didn't want to have the same old ducktail spoiler that so many other people had got. And I tried to think of a way to make it custom. The thing that came to mind was putting a brake light in there as a cutout in the letters 350Z. Easy enough, I thought. All I need to do is make a 3D printed model that I can cut out a section of the spoiler, put that 3D printed model in there. Also 3D print some resin translucent lettering to fill in the gap, and then buy a brake light thing that you can just connect up to your brake lights off eBay. Great. Quickly realized it wasn't going to be sufficient. The lights that I bought were nowhere near bright enough, and the worst offender was the fact that I'd placed the 350Z logo in the middle of the ducktail spoiler. The problem with that is when you actually mount it to the car, the middle of the spoiler points slightly downwards, so the true center, if you want to have a center line, is actually lower than center. So we decided to do it a different way. I was going to create a panel that's almost like something you could rivet onto an existing ducktail spoiler with the 350Z cut out of it in clear acrylic. Instead, we created this matrix block of lights that held 186 neopixels, and this was going to be our new ducktail spoiler light. Bright, controllable, custom. And then that opened the floodgates of the fact that I could put my neon lights and everything in there. But not wanting to be able to just set a color for neon lights, I needed to be able to change it. So we built an app, and we built Bluetooth into it. And so we made an app. And the app could talk to a HM10 Bluetooth module, and that Bluetooth module was part of the Arduino package, and all that together meant I could then go in and change the lights and some of the settings. Then I had this idea about, well, what if that was actually part of a network of systems, and therefore it wasn't something that would just have an app that control it, and we actually created a car area network and allowed ourselves to have a central control center that actually utilized a different chipset, an ESP32. So we translated all of the stuff from the Arduino and the HM10 Bluetooth to an ESP32 system. Then I had everything on prototyping breadboards and, temporary wires and buttons and all that, but we hooked it up to proper optocouplers and voltage regulators and got about installing it in a project box and putting it in the car. At that point, it didn't work. So I needed to figure out a way of making it more robust. And the obvious answer for that is a PCB. Thing is, I've never built a PCB, and although I know enough about electronics to get by, I haven't had to think what Ohm's law is in a long time and figure out how to actually build a schematical diagram, so we had to figure that out. And that's kind of where we're at now, and there's one other change. This thing is no longer going to be used. The reason is I took the ducktail spoiler out to the car today, put it in place, and the idea was I was going to mark up the new 350Z logo, and I don't like it. I don't like having the 350Z logo with it's something to do with how it looks when there's the number plate directly below it, and kind of like the sizing of the letters. It doesn't feel right. So instead, I'm going to do a big long strip right down the middle of the spoiler, which is what this bit of black tape is. That's marking where it is going to be a perspex like cutout down there. So that's what this is going to look like now. Which does mean I need to do a new one of these, but the big advantage is I'll only need 60 lights for the whole thing as opposed to 186. So I massively reduce my current power requirements. So here we are, we've reached the point where we need to do custom PCB design because the things that we've created so far aren't robust enough to use in a car. And that's kind of expected, and this is a step that I always knew we were going to have to take, but yeah. Like I say, I haven't actually done PCB design before. I do know enough about what different electronic components do, and I have to do basic calculations to figure out which ones you need to use, but a lot of this process has just been research and utilizing AI, where it's handy to do so. So let's just take a look at what I've done and what decisions I made to take that whole box of project stuff, which has actually now been taken apart. I'm sorry, he didn't live very long. And how to take all that and put it onto one board. Basically, it's been a lot. So let's jump into looking at how I managed to do this, which means it's time for the all glasses, and we've got some new ones that aren't covered in scratches. Gotta love it when you've got good glasses. When I was doing my research on which applications to use, KiCad came up a lot. It's that combination of does everything from your schematics and your PCB design. It's user-friendly and it's free. Winning combination of factors for me, really. So this is KiCad, and these are the various things. I don't think in this video we're going to look at using KiCad because I don't think I'm experienced enough in it to do a tutorial, but I will say that I did find it relatively easy for doing a lot of stuff. And when I get into it, this is, he says, this is the schematic editor for what I have ended up creating in KiCad. It looks like chaos, and I think maybe an easier way to look at it is in the PCB design, which is here. And probably an even easier way to look at that is, let's check out the 3D viewer. Okay, so this is the PCB that I've created. So what we'll do is we'll just take a look at it in this 3D view, and hopefully by the end of it, you'll understand how the circuit works. And then I'll just talk through how I figured this out with no real knowledge of what I was doing. So first off, I think it's important to note that I did this as a type where the ESP32 can just sit in here. You can get ESP32 chips and get them and implement them into the PCB itself, but then you've got to consider about like how do I connect up the computer to it, and how do I? There's just like loads and loads of additional pain in the ass stuff that you have to do. So I thought, actually, for my first time out, it's going to be easier just to put these two tracks in 25mm apart. And I'll just have it so that my ESP32 can just clip straight in. It's going to save me a lot of aggro. Then, these like light sections here are copper underneath the surface, which are connecting things, instead of just using little lines like we do have in some spots. The advantage of doing it like that is we get better heat dissipation, so it doesn't, especially around this big old boy in the middle, which is a buck converter, we don't get as much issue with heat. Also, the entire bottom is a different color, as you can see. The entire bottom is ground, so anytime I need a ground, I can just drop a little one of these little holes through, and I can ground it straight away on the bottom. That'll make life a lot easier, and it'll, you know, make you understand why we've done a few of the things. So let's just walk through the circuit, kind of from the middle out, but then we'll go from over here. So this thing in the middle is the big important thing. It's a buck converter. What a buck converter does is take an input from a range and convert it to an output within a range. This one will input anything from, I think, around 2 volts up to 17, 18 is kind of like preferred range, but it will handle up to 60 volts in a spike. So it's really good for what we're doing, because our one is generally going to be in that kind of like range under 17 volts. The way we decide what voltage it outputs is based on a couple of resistors, and they are set here. So I've got a 0.196 kilo ohm resistor and a 64.5 kilo ohm resistor. The only reason I knew which resistors to put here is, and which pins to put them to, is it's all in the data sheet, which we'll take a little look at when we've gone through this. So there are two resistors into this buck converter which set the output voltage. So if we then start over here at the VCC, this is where the car's main power circuit, the ACC switch power, will go to. And it comes down this track and switches into two parallel circuits. The bottom one is probably the more important of the two. It's an SMB diode. It's basically designed to help clamping over voltage transients to safe levels. It's a lot of big, fancy technical words to mean protects the thing it's in the circuit of against massive spikes in voltage. That's what this is going to be used for. And we actually have three of those, one here, and one here. And what they all do is on their relative circuits, they protect the thing that is being connected to each one of those circuits. So in the two cases here, the optocouplers, and in the center case, the buck converter, from voltage spikes. Then also we have a 1 kilo ohm resistor which is needed for this little LED. So there's an LED here which is just a state LED, and it's going to show us whether or not the power for that circuit is on. It's a pretty simple one. Then we get into the stuff that you can't just know, you have to get into the data sheets for the module. So in this particular buck converter, if you go through the document, which we'll take a look at in a moment, it'll tell you that if you want to have certain voltages in and certain voltages out, these are the capacitors you need around those inputs and outputs to help keep everything, in check. What a capacitor, generally speaking, does is removes noise. So if you imagine you've got a signal that's coming in that's really noisy, it'll help keep that at a nice standard level. And that's going to be really useful because we've got circuits that are switching up and down, maybe quite quickly. So we're going to want to make sure that they're at like quite standard levels all the time. So depending on the voltages we're expecting in and the voltages we're expecting out, depends on which capacitors we need. And it's all in the data sheets for that module. So this one says that we need two ceramic capacitors. So we've got one here, a 0.1 microfarad and a 47 microfarad. And then we needed a larger organic polymer capacitor, which is this big boy, the 100 microfarad. So that's it's the tallest one on the board. And they're just three capacitors, which all need to be kept, quite close as possible, really, to the buck converter. And it's the buck converter that is going to have the thing with the heat, and what is the thing that requires heat dissipation, because it's converting those voltages, which is why around here there are lots of these kind of copper plates. They'll really help disperse the heat around the buck converter. So that's our input circuit, and the input goes in to a bunch of different inputs. If we just hide the SMD models, we can see that these all go into a bunch of different circuits. That there could do with fixing, so that joins, I'll sort that in a moment. And all of these like inputs and outputs, again, all that information is in the data sheet. Then on the other side of the buck converter, we have all the outputs. We've got a couple out here, here and here, here that all go to ground. And then we've got this bunch that go into this capacitor. So it's another 47 microfarad capacitor. Again, is needed to help keep that voltage regulated. We've got the two resistors, like I say. These two are in specific pins and they set the output voltage for the buck converter. So the combination of these two in these two pins in this way, again, from the data sheet, will set this as 5-volt output. And then the rest of this plate comes round and distributes to optocoupler 1, optocoupler 2, and then if we get rid of the through-hole models, we'll see this one goes off into this hole, into this pin, and into this capacitor. And this like capacitor over here is the one that goes and regulates the voltage in and out of the ESP32. So that's where the ESP32 gets its power. Then these circuits that connect up to the optocoupler, the other side, these two are the pins, then go in series through a 1 kilo ohm resistor into an LED, and then into this pin and this pin. So these two pins are the pins that we're going to be using in our ESP32. I believe they're 26 and 27, might be wrong, but we're going into those two pins. Similarly, data sheets, when using these LEDs, they say you want to use a 1 kilo ohm resistor. So you put a 1 kilo ohm resistor in there. It's not rocket science, though it sort of is, just not super difficult rocket science. Then the neon and the brake both do the same thing. They're just mirrored on both sides of the board. So they come down, then the signal splits three ways. It goes into another capacitor, which is going to, again, try and regulate that signal into the optocoupler. It's got another SMB diode, which is going to protect that optocoupler from voltage spikes. And then SCH over here is a different kind of diode. It's called a Schottky diode. And again, very similar to the SMB, it's for protecting loads, but it looks at like flyback voltages. I'll be honest, didn't really know about that, but when I was doing my research and using AI, they all said to me, make sure you've got Schottky diodes around your optocoupler circuits to protect from flyback voltages. So we did that. And really that's the circuit, other than the outputs over here. So the ground just grounds on the opposite side. The data just goes past this pin and then connects in over here. If I get rid of the through-hole models, you can see that one goes over here. And then this 5 volt out comes through this 470 ohm resistor, just to bring the currents to the right level. And then goes over here to this connection pad, which is where all the 5 volt circuit comes from. So this whole thing here has a 5 volt circuit as well. There's an argument that maybe I could have, expanded it around here and had better heat dissipation, but it should be fine. It's only 5 volts. It should be fine on one of those single traces. So if I go backwards from this spot, in order to get this, which I've now bought, and thanks to PCB Way, they're really inexpensive. In fact, I used someone else's join link and I got the boards for free and only had to pay, I think, $5.20 for postage. So it cost me about £4 for 5 of these boards that are now on the way in black, because obviously they've got to be in black. In order to get that, we build this. Now, this isn't going to be a lesson, like I say, on how to use KiCad, because I don't consider myself an expert, yes, but it's actually not too difficult. It's just a matter of finding the right devices and connecting everything up in the right way. And I do like that if we say, for example, break this line down here, it'll tell us, oh, this thing and this thing are supposed to be connected. So as long as we built everything properly in our schematic editor, it should really just tell us what we're going to be building. And that's what it looks like in a data format. So these are kind of all the pins. This is the bit that took the biggest amount of pain, was this, which is the buck converter. There are a lot of pins that need to be connected together for various things. So like all the V pins and this VIN all get joined together, and then you have to put capacitors in between certain things, and then all these grounds have to go together, and then all the V outs have to go together. And then you've got a couple up here, which is this RT clock, this A ground. They have to go together with a resistor in, which sets your output voltage, or it sets the frequency of your output. And then this one sets the output voltage, or one of those ways round. I'll show you in a moment in the data sheet, but you basically have to connect a load of this stuff together, and it shows you how to do it, and it even shows you kind of like a recommended way of laying out these thermal plates in order to connect all the things together in the way that it wants them to be done. So that kind of stuff I really appreciated about it, because it did make things a lot easier. Obviously you can see where I turned these inputs around, and so I had to loop everything back on itself. But yeah, it's all not too bad. The big pain that I found was making sure that I had components in there that were available. So I've been buying all the components from Mouser, which is just a well-known electrical components provider in the UK, and you can download from Mouser all of these footprints, which will show exactly what size they're going to be, which is really useful. And it also, you can download the 3D views. So most of these, that because they have been provided by Mouser with 3D views, they are showing up here. A couple of them are just, I'm just using generic footprints. So we don't have the actual 3D, but you know, you get an idea. Also, I'm not really much of an expert when it comes to soldering, and some of these that you can buy are ridiculously small and would be difficult to solder. So I tried to go for some of the larger components, basically everything over 3mm in length, just to make my life a little bit easier when it came to putting this together for the first time, which is something we're probably going to be doing in the next week or so when everything has arrived. So yeah, I tried to just make my life as simple as possible, and I think one of the things that was arduous with this, but worth it in the end, was going back and forth between this design and Mouser. So if we just take a look at my basket, these are basically most of the components that I'm going to be using in this circuit diagram. I'm just making sure, A, they're available, they're in stock. Oh no, that one I need to buy a minimum order of 5,000. So I need to find a replacement for this one. But I was trying to find ones that are in stock, available, where you can buy like 5 or 2, or, you know, and not have to buy 5,000. And also that ideally had 3D views that you could download. For example, if you go onto this is the buck converter. It has this 3D mode, and you can just go onto here and it will show you what it looks like. So this is what you might recognize from those previous screens. It's the 3D model and the view that we see it in the circuit diagram, as well as the footprint. So that was really useful, and a lot of this process was going back and forth between Mouser and between here and finding the right components that did serve the purpose. So if, you know, if I need a 1 kilo ohm resistor, it's all well and good finding a 1 kilo ohm resistor, but there's thousands of them, and just, you know, whittling it down to the right one was a pain sometimes, but I think we got there fine in the end. One of the things that was really important though was these data sheets, because when you go into here it tells you exactly how to use that component. So once you'd landed on the right component, the big thing was kind of these, the pin functions. What you basically do is start by reading down the pin functions. For something like this, which has got 43 pins, there's obviously a lot of things that need to happen, but it'll quickly tell you, like, there's an A ground, which is for the analog ground circuit, and you basically keep the 2 A ground pins together and keep it separate from P ground, because P ground and A ground are linked inside the device, so they don't need to be linked outside the device. And then P ground, it'll basically tell you that you need to connect these pins to the load and to the bypass capacitors associated with the V pin and V out. Then you've got all your input switching voltages, you know, your V outs, your pH. It basically tells you what all of your pins do. But once you get a little bit further on, we'll start to get past all these like characteristics and stuff. I'll be honest, these are electrically beyond me right now. I'm sure I'll pick it up a little bit more in time, but at the moment there was kind of like nothing that I was able to gain from these, other than just checking things like the power switch range can go between 3 and 17 is like ideal for the in, and the output anything between 0.6 and 5.5, so it fits my purposes in that. Then we've got all like these characteristic things, which again I didn't really feel the need to dig into. What we do start to look at is kind of after that we get here. So it starts to tell us how to set everything up. So one of the big ones was this, adjust the output voltage. And based on the output voltage, if you just read through this, it basically says you need to put a resistor between these pins and then use this pin and connect another resistor. And it'll tell you if you want, here's the full list, depending on the output voltage that you want. So in my case, 5. These are the 2 resistors that you want to use in order to achieve that. So our set is a 0.196 and our RT is a 63.4. So when we looked at these, that's our 0.196 and this one here is a 63.4 connected between the pins as we were instructed to by this. Yeah, so really these data sheets are really useful. What I also found quite useful was using AI. It has been something that I have jumped in and out on, especially if you go back and take a look at the 5 AIs that we used when we were doing a bit of the previous work. I've used Claude quite a bit, predominantly because Claude allows you to drop in images such as this. This is just a cut-off version of what I gave it, and say, is there anything wrong with this circuit? And it actually will go through and tell you if it thinks that there are problems. It's generally pretty good. It made a few mistakes. It thought one thing was something that it isn't. It's definitely not a perfect solution, but it was ideal for a few things and for increasing my understanding of why things were done in a certain way. So for example, I have these Schottky diodes down here, these things, which are used, I was told by reading information about how to set up these optocouplers, it basically says use these Schottkeys, but I didn't know what they were about. So you could ask it, what is a Schottky, I think I spelled that wrong, Schottky diode used for when placed before an optocoupler. The Schottky diode before an optocoupler is used as a flyback or freewheeling diode protection. Protect the input LED from voltage transients induced by inductive loads. So a lot of this stuff you really need to know what the technical jargon means, and I'll be honest, I don't enough, but I do trust when a data sheet for a device that I'm purchasing says get these 3 things and put them in parallel before the optocoupler. I trust that that's what I'm supposed to do. So all being well, this is all going to work great, and in a few days, sometime this week, these things will arrive and we'll be able to see, because I've got all the components on the way as well. I'm going to have to put it all together. It's not something I've done before. I think that's going to be a little scary. I've got to figure out how to use solder paste, especially for this thing, because if you think I'm soldering them things one at a time, think again. It's not something I've done before, so we'll look at how we achieve that, having never done it before, because, you know, this is scary and daunting looking. I'm still looking at this, I'm like, there's bound to be something wrong. And maybe some of you are experts in doing PCB design, and you'll see that I've overlooked something that might well have not been overlooked had I had more experience. But I think the sensible part of my brain says this is good and it's going to work, but paranoia. I guess all we can do is wait, get these things, wire everything up, or I say wire, solder everything up, put it all together and see what happens. Best case scenario, everything works fine, doesn't blow up. Worst case scenario, I guess something blows up or sets on fire, but I think it's very, very unlikely considering the kinds of components we're using and how much circuit protection we're putting in there with the various capacitors and diodes and resistors and whatnot. Are any of you experts in PCB design? And if so, here we go, here's the money shot. Is anything wrong here or here? Maybe pause it and take a look. There'll be a full list of parts in the description as well, so if you wanted to check any of them off. But I think everything's good, I think. So we'll see. But that was my first ever look at creating a PCB in KiCad. I've got to say, KiCad, pretty easy to use. I do like how you can just, I've just pressed A there, come in and take, say, a resistor, so the letter R, and then add in a resistor, bam, and then we just wire that up, and then we just need to tell it by assigning a footprint to this resistor. And we go into here down the left and go, okay, well, we're going to do SMD resistors, which are the kind you solder onto the board then what size do we want? And this is kind of where I went back and forth with Mouser. So I'd again have to go over to Mouser and see which of these sizes it's got. And these numbers relate to its size. These are fractions of an inch, I believe. These first numbers are fractions of an inch, and then this side is it in metric. So I tried to take some of the larger ones, like I say. So 3216 metric is 3.2 millimeters long and 1.6 millimeters wide, which is whatever that is in fractions of an inch, 1206. So I tried to find ones that, like I say, were on here, and then I'd go over to Mouser and I'd have to find the same size one and make sure that it had that resistor in the ohm rating that I wanted in that size, and then that meant I could use it. Ideally one, like I say, that had a 3D model and a footprint, which then I could download, put into KiCad, and get going on there. But this is the first one of these, and I think the big important thing, I think, is going to be the takeaway for this, is if this bit all works fine, so if all of the stuff around the buck converter works fine, that's going to be a thing I can rinse and repeat use for other electrical things, because they're all going to want to come in with a VCC in 12 volts, and it's the same dirty 12 volts, and get filtered down and have the capacitors and everything that makes the signal nice, and basically getting to this point here where I've got a nice, clean, consistent 5 volt output, which obviously can be used by my ESP32, but probably a lot of Arduino components, in fact, not probably, a lot of Arduino components want a nice, clean 5 volt circuit. So if this all works fine, this whole like center, left-hand side of the diagram will be reusable for other things. So fingers crossed, that's all going to be good. But you know, all I can do at this point in time is like hope, because I haven't done this before, like I say, and it's all a bit new to me and scary, but not at the same time. At the end of the day, I'm working with 5 12 volt circuits. Like, what's the worst that can happen? And assuming it's all good, we get to make little cool box to keep it in, which is why I put these holes in the corner, in order to have it so it orientates a certain way. And yeah, plenty to come. But I think we've maybe got 2 videos left then on the light circuit. We've got one where we'll put this together, which will be coming whenever all my bits are here. So basically, as soon as all the bits are here, we're going to try putting this all together and testing it. And then the final one is going to be with this once it's done. So over the next few days, I've got to cut this thing out and build this like as a Perspex cutout, and this existing cutout all needs to be dealt with and got rid of. So that's all got to happen, and then rewire in the new lights and everything there. So that, the end of that, and combining it with this new printed and hopefully finished and beautifully made thing and putting it in the car will be the final part of the the lights video series, which is crazy because it was supposed to be a 3-part series and it's become 10, maybe 9. It's a lot of content. It's become a lot of stuff. It's taken up way more of my life than I have anticipated. Hopefully now you've realised that this is really scary. No, as long as you're RTFM, read the blooming manual, then I don't think we should have any problems. The only problem I can foresee having is the soldering of everything, but fingers crossed we can get that to go nice and smooth. If you have any comments or pointers or anything with this, or advice for what is coming next, please leave them in the comments. I'm not egotistical when it comes to this. I don't pretend to think I know exactly what I'm talking about with this, because this is new to me. A lot of the other stuff is not. This part is. So if you have any advice for this, stick it below, especially if it's things you think that other people can read in the comments and take away and, you know, utilize when they're building these circuits for their cars, because, you know, we don't want people to be putting things into their cars that are going to be potential fire risks or whatever it might be. So just from a safety perspective, let's try and share information. So if you've got any good tips, advice or thoughts about this, like I say, throw them in the comments because I'd love to hear them. Otherwise, we've got a video on the duckbill spoiler preparation coming in the next day or so. So there's plenty to look forward to. Whatever you do with the rest of your day, folks, have a wicked one, and I will see you in the next video. Take it easy, peeps. Bye-bye.